So with those three elements of fire being required for combustion to take place, obviously one of the most important elements of it is the concept of fuel. Right? You need something to burn to actually to release that chemical energy, and in most cases, vegetation, and especially dried out vegetation that has lost a lot of water content is that fuel. And so wildfires, you could say one of their natural service functions is to remove vegetation from the landscape and allow new vegetation to thrive. You could say that fire even reverses the process of photosynthesis. Now think about it for a second. If you remember from biology class what photosynthesis is, that's where plants take in, let's go with green right here, they take in carbon dioxide, right? And then they breathe they release, or you could say they breathe out oxygen, right? That's why if we were to ever colonize another planet or another moon or something like that, you wouldn't have to have vegetation because they produce oxygen, they breathe in carbon dioxide. Well, fire is just the opposite of that. It requires that you put in oxygen, and one of the byproducts I lost my train of thought. Combustion. Sorry, one of the byproducts of combustion is carbon dioxide coming out. So fires are kind of the opposite of the process of photosynthesis, and so like I said before, let's see here, we have, let's say, a carbon. Now this is a simple hydrocarbon, carbon and 4 hydrogens. We call that methane. All right, plus an oxygen, which travels around in pairs, so we call that O2. When these combust, you have 2 H2Os, so these oxygens go over and one of the oxygens joins with, do I have that, I'm sorry, there should be 2 oxygens right there. One of the 2 of these oxygens come over and join with the 2 hydrogens and make 2 water molecules, and you also have plus 1 CO2. I'm a little rusty on my chemistry right here. So you have methane and you have oxygen that you start out with, and when it combusts, energy is released and light is released, and you come up with water or water vapor, which we have right here, and also carbon dioxide is released as well. I'm trying to do this balancing in my head, and I think I have that right there. Other gases are released. You've got nitrogen oxide and carbon monoxide and even some methane, which is what this is right here. Not all of it is burned, but in most cases, predominantly water and carbon dioxide are released, which seem like pretty harmless things. It's not like they're pollutants or anything. The water we certainly need in the atmosphere, and carbon dioxide is important as well, but of course, too much carbon dioxide we know can contribute to global warming. So we're going to look at 3 phases that are required for a wildfire to take place. And really it could be any fire, any combustion. But these 3 phases are going to be pre-ignition, combustion itself, and extinction. You know that if you try to light a piece of paper on fire, it doesn't light right away. You need to kind of have it in that fire, that flame a little bit before the paper will ignite. You can think of that as pre-ignition, and some of the processes that are going on are getting the paper ready to start catching fire. Combustion we just talked about, we'll talk about in a little more detail. And then extinction, what actually happens to cause the fire to go out. One of those 3 parts of the fire triangle go away. So pre-ignition, what's going on right here? Well, the fuel is being heated. That's why you need heat. Heat. I guess I should have written that in red, but you need heat to sustain a fire, because what heat does is it takes the fuel that is not quite ready to burn yet, and it brings it up to a temperature favorable to ignite. For example, what does that bringing up to temperature do? Well, it causes water to kind of boil out and evaporate away. You ever try to light a piece of wet wood? It doesn't work. You need dry wood. You need dry fuel, because water is something that sucks heat in, and it prevents the fire from taking place. So if you want that fire out of there, you need to kind of burn it out by heating it up first. Volatile compounds, if you remember what volatile means, that means compounds that are easily turned into gases. And really, when you see a fire burning, what a fire actually is it's a glowing gas. That this thing we always see, when we think of a fire, right there, that kind of flickering glowingness is really a gas that is giving off light. All right, and so we want, in order for burning to take place, you want volatile compounds to start coming out and get ready to burn. Solids don't actually burn. It's really the gases that they give off that burn. So any compound that is easily turned into a gas or into a vapor, that needs to be heated up, and so that takes place in the process of pre-ignition. Heat can also take compounds that are in the fuel, whether it's wood or paper or whatever the case may be, and actually get it more prepared for burning. Pyrolysis, heat divided. That means taking a compound that maybe isn't ready to burn, and that heat will chemically break it down into more easily burnable compounds. And so pre-ignition either heats the fuel so that it's the gases that are ready to burn are ready to burn, or it takes it and kind of breaks it down so that it turns into gases that could burn more easily. So say you have a fire taking place right here, like right over on the right, okay? If there's trees and grass and that kind of thing over here, what that fire does is, even though the burning is taking place over here on the right, oops, I didn't want to scribble on that, oh well. What it does is it causes heating because of radiation. All right, so even though the fire isn't burning this stuff quite just yet, radiation is coming off of this fire, and it's preheating the next amount of fuel that is ready to be burned right there. So that all is what takes place in the process of pre-ignition. So let's say that our area, our fuel, our grassland or woodland has been pre-ignited. It's reached a temperature to the point where it's ready to burn. Then the next stage is what we call combustion, and this is what we usually think of when we think of something burning. That is the actual flames that take place, the heat that is released, and the light that is released, and the red and the orange and the yellow flickering. All that takes place with ignition. All right, now the pre-ignition is where energy is absorbed by the fuel and is getting brought up to temperature, ready to burn. What combustion does, it's a chemical reaction. It releases energy. You can think of pre-ignition as being kind of like a physical reaction, like you're just heating it up and heating it up and heating it up. Combustion is where you actually have it chemically changing, and so when, like I said before, those methane molecules and oxygen turn into water and carbon dioxide, you have completely different chemicals that they're turned into, and in that process, energy is released. All right? That's why you feel heat from fire. That's why you see that light from fire. Light and the heat are both a form of energy. And so heat and light are liberated, they're given off, and what that energy that is given off does is it pre-ignites other fuel and makes it ready to burn as well. Ignition doesn't always lead to wildfires. You actually need enough fuel, and sometimes you might have something that is ignited, but if there's not enough fuel around, it'll quickly die out through the process of extinction. We actually need lots of ignitions in order for mature vegetation to take place. So what happens is when simple plants or simple fuels burn, that carbon goes into the soil and makes it more ready to support more mature vegetation. All right, so you can't have a forest without grasslands. You can't have grassland without simpler vegetation. And what wildfires do is it makes the land ready for more vegetation. Every 50 to 100 years, every single acre of land is struck by lightning. All right, so an acre of land is maybe the size of your backyard, or maybe your property, maybe a little bigger, maybe a little bit smaller. But on average, every 50 to 100 years, every single acre of land is struck by lightning. By the way, there should not be an E in lightning right there. Where is it? It's Lightning. So if you think about it, with this time scale, the amount of wildfires that are set by human interaction or human causes really aren't as significant. That is, fires would take place anyway because the lightning strikes, like I said, every acre of ground between every 50 and 100 years. All right, it's going to burn anyway. But the good thing about what wildfire does, especially that is set by lightning, is it reduces future wildfire chance because you burn out an area, and it's less likely to burn after that because you've removed all the fuel. Okay, so combustion, it really isn't a once and done process, but it's a process that keeps occurring. Like I said before, the fire that is taking place, the combustion that is taking place, is actually preheating the next round of fuel that's ready to combust, and so it recurs repeatedly as the wildfire moves across the landscape. All right. Now there's a couple different kinds of combustion we're going to talk about. We've got flaming combustion, where you actually have flames, and that's what you normally see when you see a fire. All right. Early fire, lots of energy is released, and so lots of heat and lots of light, and so you see a lot of flames. Temperature conversion of fuel into heat. All right. So that the chemical reactions are taking place very, very quickly. So as the volatile gases, that is what is actually burning, as they're removed from the fuel, what happens is you've got all kinds of non-combustible material that is left behind. Stuff like ash, and I'll write this in red. You got ash and charred wood and stuff like that. Well, that stuff doesn't always burn, and so what that does is it makes sort of like a barrier to prevent the flaming combustion from moving too quickly. All right, so the stuff that doesn't burn acts as sort of like a roadblock or like a speed bump to more fast burning. If the fuel that you have burns very quickly and very completely, then you're going to have a very rapid combustion process. But in the main, you have a lot of stuff that is not burned, and so like I said, that behaves kind of like as a speed bump. You also have what's called smoldering combustion. This is where you don't necessarily have any kind of flame. It's still taking place. You still have conversion of chemicals into heat, but maybe not into light, and so you don't see any flame right here. It's still taking place. It's still being broken down, just not at as rapid a rate as it does with flaming combustion. All right, so right here is a diagram of the kind of three different parts of a wildfire. You've got the fire taking place right here, obviously. What has already been burned is still smoldering, you could say, or still kind of glowing. It's still giving off heat, very much like, let's say, if your mom or dad is grilling out back, or if you grill out back. You don't necessarily want flames coming up, but you want the heat given off by those smoldering charcoals. That's what's taking place right here. There is your flaming combustion. Obviously, that's what draws most of your attention. And if you get your preheating and your pre-ignition going on right here, that is the radiant heat, that is the infrared radiation coming off these flames right here, are prepping this fuel and getting it ready to burn. And that's going to be the next stage of the wildfire process. Okay, so as wildfires combust, there's a couple different processes that sort of control how heat is transferred in wildfires. First of all, the topography of the region, where if you're upslope or downslope, or if it's flat, that'll determine how readily air can come in and sustain the combustion by providing that oxygen. All right, how well is heat transferred? All right, well, are you going upslope? Is convection, that is the upward movement of air, is that playing a part? Is heat transferred through radiation, which requires the next amount of fuel to be preheated. How well does convection? How well does radiation take place in that topography? Okay, the more convection, the more radiant heat that is released, the next round of fuel is being heated up, and so the ability to which that can take place is one thing that determines how fast wildfires can transfer. This is This is kind of interesting how fires sustain themselves. As gases become less dense and rise, like with convection, all right? Hot gases rise up. Well, as they do, they create sort of like a vacuum in here, right? As air rises up, you need something to replace that vacuum. And so what that does is that draws more fresh air in from surrounding areas, from there and there, and provides more oxygen to sustain that fire. All right, so it's kind of interesting how fire kind of gives itself its own oxygen supply, causes gases to rise up, pulling in more gases from the left and from the right, and that's what takes place in combustion. All right, and lastly, we have our final stage, which is extinction. That is when the fire actually dies out. And so what happens is you've removed at least one of the elements of the fire triangle from that wildfire. Combustion, flaming combustion, also smoldering as well, goes out. You probably know that from kind of fire advisory information that many wildfires, that is human-set wildfires, are caused by smoldering that wasn't quite put out. Like say somebody's a campfire wasn't completely put out. It's not like they walked away from it still in flames, right? That's not the case, but rather it still had kind of like this just sort of a glowing hot smoldering going on, and that right there is still combustion. It still has the ability to cause other fuel to combust and turn into flaming combustion. So when both of these kinds of combustion go out, we call that extinction. All right, like I said, you've either removed some of the heat for pre-ignition, you maybe removed some of the fuel, or maybe even you've removed some of the oxygen that enables that fire to keep going. Any one of those things removed causes the fire to extinguish itself. All right, and so just a minute ago, I talked about how topography can affect how well the fire moves, or how well pre-ignition takes place, so that the next round of fuel can burn. Let's say you have a flat surface right here. All right, you got the fire and convection causing air to rise up, and it draws in a draft of fresh air right there. All right, also from the side as well. That's why high winds are oftentimes noticed around large wildfires, because really the fire itself is drawing the wind in. All right, well, the pre-ignition is just taking place just from the radiant heat right there. All right, so this next round of fuel is being heated just by being kind of in proximity to that fire. It's not that it's being heated by convection, no, because that heat is rising up, but it's just the radiation coming off these flames is preheating that next round of fuel. What if you've got a flat surface and wind? Well, wind really exacerbates fire. All right, that provides lots of oxygen, O2 coming in here, even without the fire drawing it in. So that really fans the flames of the fire, which is kind of why we have that saying: you fan the flames, you provide it with more wind, and so that blows the fire towards the next round of fuel, causing even more preheating and more pre-ignition, and allowing it to burn even better. Well, let's say you've got a fire going up a hillside. All right, even if you don't have wind, the fact that the fire is kind of along the same line as the hillside right there makes it easier for this next round of fuel to be heated. And so between radiant heating and just being in more close proximity to those flames, this stuff is going to be pre-ignited very easily and get ready to burn very rapidly.